Okay, hello and welcome to my channel. Today we're gonna continue to talk about the hydrogen atom, and this time we're gonna try and get the energy, get a grasp of the energy to see how it's gonna be calculated, how it's gonna look like. Yeah, let's first by introducing our relative mass and our center of mass. So first is the relative mass, which is ME and P, the product over the sum. Next is our center of mass, which we're gonna write as the big M, which is just gonna be the sum between ME and MP. Okay, so from here you can transform your alpha and beta as well. So alpha would be mu on top of MP or ME. No, this is ME. This is ME, and beta is mu on MP. Right. So from here, you're gonna write your P of E and P of P again as well. This is ME over big M, the big P plus small p. That next is our this is gonna be the minus sign instead. This is the big P and that is the small p. Right, so from here you can sort of transform your Hamiltonian, or more specifically your kinetic part of the Hamiltonian or your kinetic operator, into something new. Here would be, well, your previous kinetic operator, your t hat, is previously pe squared over 2me plus pp squared over 2mp. Okay, so with this thing right here, you can factor out the 2m. This is mp. Okay, you can factor out the 2mp to put the mp on top of that one, and that one would just be the factoring out the me. So basically 1 over 2 me, your p squared is gonna be me m p plus p, big P plus small p square, plus over 2mp p over m p, this is big P minus small p square. Okay, so this you can, well, tidy it up to get something like this. And this would be the form that we're gonna use. This big P over 2m small p over 2 mu. This would be the form that we're gonna use. Okay, so this is your kinetic operator in your Hamiltonian. Now your Hamiltonian can be rewritten as the p squared over 2m plus small p squared over 2 mu square, plus your v, this is the relative distance. Okay, that would be your Hamiltonian. Okay, now let's put these into the time-independent Schrodinger equation and try to find the energy to see how it looks like. Right, so our Schrodinger equation be like this. and your wave function. Now, this is previously of big X and small x. We can split these into, well, the psi center of mass of big X and the psi relative of small x. Okay, so that would be way easier to deal with what we just get right here. Okay, so we're gonna put these into our time independent Schrodinger equation. First one is gonna be, let's take the pen, my pen died again. First one is gonna be the center of mass part to m psi RL, where we would like to group, but I'm gonna do that later. Relative, gonna take the relative part, of course. What? Relative, gonna take the psi RL, Cm. Next is our potential, which also is dependent on the relative position between the two particles. So that would also take the psi RL, or psi relative, and the psi Cm is outside. All these would equal to E psi Cm psi RL. Okay, so what I said about grouping is that you want to take these and kind of divide them into groups, so that when you divide the entire thing by the wave function, you would get the 1 over the desired piece that you want. So for example, you divide the whole thing and you now preserve your psi, say psi Cm, and when you get the energy, you can just put that 1 over psi Cm over, so E would now acting on the psi Cm. So that's what I meant by grouping these and divide it by the original wave function before splitting. Okay, so now we divide. What we get now is 1 over psi RL is gone, so 1 over psi Cm of our chunk P squared over 2m Cm. This part, I'm just going to group them since they have a common factor of psi Cm outside. So this would just be 1 over psi RL P squared over 2 mu psi RL plus V of absolute X psi RL. Okay, so this is gonna equal to the energy. Right, so from here you can see that these two chunks are gonna represent our center of mass wave function and our relative wave function. So you can divide these two into like chunks. This is gonna be the center of mass chunk and this is gonna be the relative chunk. So from here you're gonna get that our P squared over 2m psi Cm is gonna equal to E psi Cm. Right, so that's why I tell you to, well, take this part out, so get the chunks. And next one is P squared over 2 mu psi RL plus V of absolute X psi RL equals to E psi RL. Okay, so that is it. Now we've got a grasp of how the energy would distribute here with center of mass chunk and relative chunk. Right, so that would be it for today, and goodbye.